So yeah, I was saying the bounds of integration when they match, if you have an integral minus an integral, you can write that as one integral of the function minus the function. We don't really have, I could draw a picture of why this is the case, but for now just take it for granted that it is. We'll see better reasons why later. A reason that this is kind of an unsatisfactory way of writing it is when I compute this integral, if I want to compute this with a calculator, the thing I need to graph is the integrand. The integrand, that's the word for the thing you're integrating, is 4 minus x squared. I need a decent graph of that. And I need to say, calculate the integral from -2 to 2. And it's showing me that region. And the thing that's weird is this region doesn't look like the region that I wanted the integral of. If I had graphed 4, and I had graphed x squared, I would see the rectangle picture, and then I would see this picture, and I would understand that when I subtract them, I get the correct thing. Doing it all at once is, I guess, less typing, because I only have to tell my computer to calculate one integral. The answer it's giving me is 10 2/3. Can I do that? That's 32 over 3. So we have an answer. The thing we saw in the picture wasn't quite the same image. It was, I guess, basically the right image but upside down, so I can see why it has the same area. For other graphs, it'll be more different, and it's giving us the right answer, but it doesn't feel like I looked at the answer. Like, there's a little bit unsatisfying, but it's giving us the right answer. Don't feel weird about that fact. Let's do a slightly messier example of the same thing. Let's find the area of the region bounded by, I have it written down here, 10x to the 4th minus 9x squared plus 3x and y equals x. What do I get when I graph these? 10x to the 4th minus 9x squared plus 3x. And the other function is x. Graph it. Okay. It looks like this thing stays above it. All the interesting stuff is happening pretty close to 0, 0, so I can zoom in. What's going on here? That looks a little better. Ew, ew, okay. Yuck. So we have, let's copy, paste. Where do those graphs intersect? How many times do they intersect? X squared and 4 only hit each other twice, so there were 2 bounds of integration. These guys intersect here, and once at 0, yeah, if I plug 0 into both of these, 0, 0 is on both of those graphs. There's another point here, there's another point here. There are 4 points where they intersect. And, even worse, if I try and set these two equations equal to each other, I guess I'm moving that to the other side. 10x to the 4th minus 9x squared plus 2x equals 0. I guess I can factor an x out of that. 10x cubed minus 9x plus 2. But I'm trying to solve this. It's a cubic. I don't think we're likely to get a solution. I'm never going to tell you to solve a cubic unless something nice that makes it easy. Like, if there was another x you could factor out, you'd be left with a quadratic, and you can do a quadratic. But yeah, this is hard to solve. And we're going to be using our calculator to get the integral anyway. We might as well use our calculator to get what are the points where these intersect each other. Hey, this is a thing your calculator can do. In that same calc menu, one of the options is intersect. You can use that to say, like, the thing you're doing when you intersect is say, hey, tell me where these graphs intersect each other. If I had graphed 5 curves, I would need to answer the question, which 2 curves are you asking where they intersect? I have only graphed 2, so that's not complicated here. By using up and down, I can cycle through all the y values. Up here it says y1, y2, y1, y2. It's going between those two graphs because those are the only two graphs I graphed. So the first curve, I'll make y1 the first curve, y2 the second curve. You hit enter, enter, and it'll automatically do that. And then it says guess. These graphs intersect each other at 4 points. I want to move over here to say, where is the point that I think they intersect? It looks like there's one around here. I'll say that is my guess. And it put some real effort into finding that point. It did a bunch of zooming in. This is too far to the left. This is too far to the right. It got me a bunch of digits. The places where these intersect are 0.8077. This one we know was x equals 0. There's 2 more of these points to find. I'll go back into the Calc Intersect menu. First curve, second curve. I only graphed the 2 curves, so I can sort of mash through that pretty fast. There's a guess that it looks like they intersect each other around here. I'll use that as my guess. What's it finding as the answer? 0.237. And then there's another one over here. Dear calculator, calculate the intersect of the first curve and the second curve, but this time my guess is that it looks like it's way over here. One of them was at 0, I already know that one. Negative 1.0447. Cool. So, the thing we want to do to compute the area, I never wrote this down, did I? The thing we computed was the integral from -2 to 2 of 4 minus x squared. In general, the thing you want to integrate, so for the area between 2 curves, you're usually setting your integral up as the left edge. They sometimes call this a pinch point, because usually it's because the 2 graphs are pinching together at that one point. I've seen graphs call this a cigar-shaped region, where it's sort of pointy at the ends and fat in the middle. Sometimes the instructions will just tell you cut it off at x equals -1. So the word pinch point isn't the right word for all functions. Of the top function minus the bottom function. This is what we want to do to find the area between 2 curves. And when the bottom function is the x-axis, that makes this a 0, and that's a regular integral. So in our case, we want the integral from somewhere to somewhere of something minus something, and part of our problem is the top function and the bottom function keep switching places. Here, y equals x is the top function. Here, y equals x is the bottom function, and that ugly curve is the top function. Here, x is the top function again. So we have 3 different regions, because who is the top function keeps switching back and forth. So I need to treat this as 3 separate integrals. I'm going to integrate from negative 1.0447 to 0 of my top function is x, minus my bottom function is 10x to the 4th minus 9x squared plus 3x. Plus, I need the integral from 0 to, what was that point? It was 0.237 of, now they switch places, 10x to the 4th minus 9x squared plus 3x dx, minus the integral from 0, not 0, now from 0.237 to 0.8077. Dang it, I forgot the minus x. Top function minus bottom function is x. And now it's back to x minus 10x to the 4th minus 9x squared plus 3x. It's worth noticing that this function and these 2 functions are basically the same. They're off by a minus sign. So I can do these basically using the same one function as long as I remember to account for the fact that the minus sign on the other. Let's try that.